Let's get started. So today we're going to continue our discussion of value functions. So first, a few quick logistical notes. Homework 2 is due next week on Wednesday, so hopefully all of you have gotten started on that. And then the project proposal deadline is the week after that. So the proposal, the more detailed final project proposal instructions should be up now or will be up very shortly, so do make sure to look at those. We have some specific guidelines this year about how we want the proposal to be structured to make sure that you cover all the important points, and also some details about kind of a peer feedback system that we'll have for the proposal so that you get plenty of feedback on your proposal from other students before you get started on your project to make sure that it fits the scope and so forth. All right, today's lecture. So on Wednesday, we ended on a kind of maybe a somewhat sad note about how Q-learning and fitted Q iteration style methods are in general not guaranteed to converge under function approximation, and that even though there's this very nice sort of theoretical backing for the tabular version of these methods, in the case of deep neural network function approximators, it seems like things are actually a little bit pessimistic. Today, we're going to learn about practical algorithms for Q-learning, and we'll learn that actually in practice, these methods can be very powerful and can allow us to very efficiently solve some very difficult problems. So we're going to talk about how we can make Q-learning work with deep networks. We're going to talk about kind of a generalized view of Q-learning algorithms. So there are a variety of different Q-learning style algorithms, but we can generally represent them in kind of a unified framework where different parameter choices actually correspond to different methods. We're going to talk about some tricks for improving Q-learning in practice. Some of these tricks are, somewhat heuristic, but some of them are actually motivated by some, reasonable theoretical backing. So we'll discuss those probably in the second half of today's lecture. And then we'll talk about how Q-learning style methods can be extended also to continuous action spaces, and there are a few different choices for how to do that. So the goals for today's lecture will be to understand how to implement Q-learning so that it can be used with complex function approximators like deep neural networks. Understand how to extend Q-learning to continuous actions, and talk about a few other practical considerations. Okay, so let's recap a little bit from Wednesday. So on Wednesday, we talked about this fitted Q iteration algorithm and an online version of it, which is the classical Q-learning algorithm. If you hear someone say Watkins Q-learning, they're referring to the online Q-learning algorithm. So these methods, broadly speaking, you can represent all of them with this kind of three-step process where you have inner and outer loops. So you have some kind of data collection that you're doing with some policy. That's basically the orange box in our RL algorithm anatomy. And the interesting thing about Q-learning methods that we learned about on Wednesday is that the data collection policy does not have to be the same as the current policy. And in fact, there are a few different choices for exploration strategies you could use in step 1 to collect your data. And then there is this loop, this inner loop, which, if k equals 1, this inner loop might not be a loop at all, but in general, you might have k greater than 1, where you alternate between computing target values for the points in your buffer. And these target values are basically the Q value that you get by backing up your old Q function estimator. So this is a bootstrap estimator with one step. You take the current reward for that transition plus an estimate of the next value function, which you get by maximizing the Q function at the next state. So that gives you these target values y. And then you regress onto those target values, that's step 3, by finding the parameters of your function approximator, the weights of your neural network, that minimize the difference between the Q value at state S and action A and its target value. And again, you can choose to do this minimization all the way to convergence, or you can do it for one gradient step, and that results in slightly different methods. So for example, if you opt to have k equals 1 and take one gradient step over here in step 3 and collect only one data point in step 1, then you get the fully online version of Q-learning, where you first make one transition, which means you pick one action using your exploration policy, you get one transition, you compute the target value for that one transition, and then in step 3 you take one gradient step using that transition. So that's n equals 1, k equals 1, s equals 1, and that gives you the classic online Q-learning. Of course, you can opt to do each of these steps different numbers of times, and then you get different algorithms. So this is the method that we covered last time. So what's wrong with this method? Well, the biggest thing that's wrong is the thing that we talked about at the end of lecture last time, which is that it doesn't converge. But more practically, we can look at what are the things that are particularly problematic in preventing its convergence. Well, there are kind of two big things that are troubling about this algorithm. The first one is that step 3 is not really gradient descent. So if you remember, we discussed how even though this looks like the gradient of some squared error between q and y, the fact is that y actually depends on q, and we're ignoring that dependence, which makes this not quite gradient descent, right? We're ignoring the gradient through the target value. So that's one potential source for trouble, and we can find ways to, not to fully solve it, but to mitigate its ill effects. And the other source for trouble is that in the online version of this algorithm, if you're collecting data from your exploration policy in step 1 by actually taking a step, training on that step, taking another step, and so on, this is a little more subtle, but the steps are actually correlated with each other. So the thing that I see 1 minute from now is more related to the thing that I'm seeing now than to the thing that I saw yesterday. So these are temporal processes, so these data points will be correlated in time. And usually, stochastic gradient descent style algorithms assume that your batches are decorrelated. If your batches are correlated, then you can have some trouble in getting the algorithm to behave properly. So we'll talk about how to address this correlation problem as well. In fact, that's what we're going to start with. So what is the problem with having temporally correlated samples? So this is, I just kind of simplified the algorithm a little bit to just plug in the value of y here, just so it comes down to 2 steps. You take some action, observe the transition, take a gradient step on that transition. Take another transition, take a gradient step. Another transition, another gradient step, right? So these sequential states are strongly correlated. Of course, states that you see time step to time step are more similar to each other than to other states. And the target value is always changing. So what you're actually going to get when you do this is you're kind of going to locally overfit to each region of the state space. So maybe this is the path that you're going to trace out when you behave in the world. For the first 3 states, they're over here. So your Q function will become pretty good at representing the Q values over here, probably at the expense of representing the Q function well at other states. Then you move on to this region, it becomes good there, kind of forgets about this part and forgets about this part, and so on and so on. So it's sort of continuing to locally overfit to little parts of the state space, forgetting the others. So how can we address this? Well, one thing we could do is we could go back to the actor-critic lecture, and in the actor-critic lecture, we actually had pretty much the same issue with the online actor-critic algorithm, and there our solution was to use parallelism. And you could have a parallel Q-learning algorithm as well. You could have, for example, multiple workers simultaneously collecting data, and these workers, of course, are then independent of each other, so if they're all doing different random transitions, then they're going to see different states that are in fact decorrelated. So you could create a batch from each of these decorrelated workers, and that will let you have a little bit lower correlation. So you can do that. And of course, as we talked about in the actor-critic lecture, you can have an asynchronous version of this with a parameter server and all that stuff. We'll talk more about parallelism in RL later in the course, but this is one way to get decorrelated batches, yeah.
But isn't it still true that the next step would still be correlated?
Yeah. So the question was, isn't it true that the next step is still correlated? Yes, absolutely. So this isn't going to give you batches that are completely decorrelated from each other, but it will give you batches where the different samples within the batch are decorrelated. So the workers are independent, but of course, time step after time step, there is a lot of correlation between the states you see. If you have enough workers, then that tends to mitigate the problem. Okay, there is actually another much simpler solution with Q-learning, which we could not use with the actor-critic algorithm. So the actor-critic algorithms were still on policy. The Q-learning algorithm is off policy, and that gives us another solution to this correlated sample problem, which is actually simpler, and it's sometimes referred to as replay buffers. So to try to kind of get some intuition for this solution, let's first go back to the full kind of fitted Q iteration algorithm that I described before. So in the full fitted Q iteration algorithm, step 1 collects some data set using some policy, and this step 1 might collect 1 sample, or you might choose n equals like 1,000,000 and go out and collect 1,000,000 samples. And then in this inner loop, you're basically just training on those samples. And that was fitted Q iteration. And we talked about how online Q-learning is a special case of that, where you set n equal to 1, k equal to 1, and so on. So the online is a special case. And of course, any policy will work for step 1, provided that policy has broad support. So that gives us a lot of freedom in choosing how we get our data. So we could, for example, just like not collect any data at all after the first round. So we could say, let's just grab a bunch of random data, stick it in a buffer, and then forget about ever interacting with the world again and just train on that random data. Now that random data might not actually cover all the regions that we might want to visit, so that might not be a very good algorithm. But if you collect enough random data, eventually might be a very large amount of data, but eventually you'll have enough that just with random data, this should in principle work. So you could just load the data from the buffer over here and not even bother collecting anything more. That basically amounts to setting k to be such a big number that all of training just amounts to crunching on the same data set. And that's a perfectly legitimate way to do fit acute iteration. Just, it might not work very well because you might need a very large amount of that random data to adequately cover the space. And you can, of course, still take one gradient step over here, in which case your algorithm just amounts to, load a batch, take a gradient step, load a batch, take a gradient step. Basically stochastic gradient descent, except that it's not really gradient descent due to the target values. Okay, so that you can kind of, in a cartoony way, you can write out that algorithm like this. It's sort of like online, but not really online, Q-learning with this, where you're just loading from a buffer instead of interacting with the world. So you can say step 1, sample a batch from the buffer, step 2, take a gradient step, and then just repeat this process. Not a very good algorithm, but as a thought exercise, it's still an instance of fit acute iteration. So given enough of that random data, it should still work. So now the samples are no longer correlated, because when you load those samples from the buffer, unlike the process where you're actually interacting with the world, where things have to happen in order, you can load things from the buffer in any order you want. You can load them randomly. You can force them to all come from different trajectories, whatever. So you can make sure that this batch is as decorrelated from the previous batch as you want, and that the samples inside the batch are as decorrelated from each other as you want. And that's very easy to do when you're just loading things from memory. And you can load batches of size greater than 1, which means that unlike in online Q-learning, where you had to take steps on exactly one sample at a time, here you can load up a batch of some size and take a step on the whole batch, which will also reduce the variance of your gradient. So that'll give you better gradients. But of course, you have to be a little more careful about where your data comes from. So while you could do this thing where you collect a huge amount of random data, in practice that's a very bad algorithm to use, and you can do a lot better. But of course, you have a lot of freedom in doing a lot better because this algorithm doesn't really care where the data came from, so long as it has the full support and so on. So all you have to really do is you have to periodically feed the buffer. So instead of just pre-populating it initially with a bunch of random stuff, let's actually just continue to feed it. But as far as this algorithm is concerned, all it's doing is loading from the buffer. And there's some other guy who's feeding that buffer periodically to try to find better states, perhaps using the latest policy with some epsilon greedy exploration. So now you still have this big buffer of transitions. You're going to be crunching on that buffer, basically alternating step 1 and step 2, loading a batch, training on that batch, loading another batch. But now you can have another process that's going to go out and interact with the world. So every once in a while, this guy grabs the latest weights from the policy, creates this epsilon greedy policy where with some probability you just take a random action, goes back out into the world, and brings back a little bit more data. And hopefully this guy will be a bit smarter than a totally random policy, so the data that he brings back over here will visit the regions where you want your learning to concentrate. So maybe if you're trying to navigate some maze, the random strategy will not actually get to the exit of the maze, but as your policy gets better and better, this data that it brings back will explore the regions on the way to the exit from the maze a little bit more, and this process will make more progress. Okay, does anybody have any questions about this?
You still assume here that there is an infinite number of states and actions?
So the question was, you're still assuming that there's an infinite number of states and actions. Yes, this is totally legitimate for an infinite number of states and actions. And in that case, the way that we have to think about it is we have to think about distributions. So while you might have an infinite number of states and actions, you would hope that when your Q function is trained on distributions of data that are similar in some sense to the distribution that it will see at test time, which formally means that at convergence they'll match, then everything will be good. And that's because machine learning generalizes, right? So if you see things from a similar distribution, you'll do well on them. Okay, so now we can put this all together and actually write out an example of an actual Q-learning algorithm with a replay buffer. And it's going to look very similar to our fitted Q iteration. We're just going to say, well, let's collect some data set using some policy, collect some data, drop it into our buffer B. So we're just taking the union of what was in the buffer before and this new stuff. So that's this process. Then we have another process which is going to sample a batch from that buffer. So you can kind of draw this as an inner loop, but it could even be a separate thread. Sample some batch, and then take a gradient step on that batch. Of course, remembering that this is not quite a real gradient. And maybe this thing you do k times, and then occasionally you pop out. So if you do k equals 1, this is actually the most common way to do it. Larger k can actually be more efficient in terms of the amount of data you collect, but a very common choice is just do k equals 1, in which case you just immediately pop out and collect more data. And while this might look an awful lot like online Q-learning, it is different in a very important way. Because even for k equals 1, the learning process looks very similar to online. You collect the data point, you compute some target values, you train, except that you're not necessarily computing the target values for the data point you just sampled. The data point you just sampled in step 1 just got dropped into this buffer, and then you sample a batch at random from that buffer. So the batch that you actually sample in step 2 might not even contain the data point that you collected in step 1. And that's what's giving you the decorrelation. So you could completely decouple these processes, but a very easy way to implement this is to just implement it as though it was online learning. So do this for k equals 1, but you're not actually necessarily using that data point in step 2. Okay, so this is basically the structure as far as replay buffers for the deep Q-learning algorithm that you'll implement in homework 3. I guess at this point I should ask, does anyone have any questions about replay buffers before I move on? Okay. So now I'm going to talk a little bit about the other issue. The other issue is that, okay, so this one we'll address by using the replay buffer, but the other issue is that this is still not gradient descent. So this thing is still a problem. So let's talk about the other issue. We can't completely solve the other issue, but we can mitigate it with some tricks. So to try to motivate this next part, let's think about how Q-learning relates to regression. So Q-learning appears to be solving a problem that looks an awful lot like a regression problem. Like this thing down here, this looks like the gradient of some mean squared error regression objective where you're regressing this thing onto this thing, except that the thing you're regressing onto actually depends on the thing that you're learning, which is kind of the catch here. And of course, if I write it out in the form of the full fitted Q iteration algorithm, this becomes even more obvious, because in step 3, I could in general take more than one gradient step, and I could even minimize this whole thing completely to convergence, in which case it looks an awful lot like a regression problem. Of course, I usually don't want to run this all the way to convergence every single time, because my targets are going to change, so I might as well not waste all that time running this thing to convergence, and I might overfit anyway if I have too little data, so I usually don't actually want to do step 3 this way. So if you do the one gradient step, you have this moving target thing. If you run it all the way to convergence, then it's very inefficient and might overfit. So you kind of have problems either way. But the nice thing is that at least if you do this argmin thing, then it's a perfectly well-defined kind of stable regression problem. So even though it might overfit and it might be inefficient, at least this part, step 3, is stable, meaning that it will find the solution that minimizes the difference between Q and Y. That might just not be quite the solution you want. So the intuition is that we kind of want something that looks a little more like this, in the sense that it's regressing onto some stable targets that aren't changing all the time, but without having to actually run the regression to convergence over here. So what we can do is we can introduce this thing called a target network, which will basically make this gradient step look a little bit more like regression onto a stable target that's not changing all the time, but still let us take one step and then go around in this loop. So the idea is actually very simple. And I'll just outline the algorithm here. So I'm starting at number 2 for a reason, because number 1 is actually above this. So we'll have an inner loop where we're collecting the data just like before. We're sampling a batch from our buffer. We're taking this gradient step, except that now our target value is not computed using the parameters phi. It's computed using some other parameter vector phi prime. So that basically decouples the target from the parameters that we're learning. So we have some other parameter vector phi prime that we're using to compute this, this right-hand side of that equation, and what we're learning is phi. And what do we use for those target parameters phi prime? Well, what we're going to use is we're going to use a lagged version of phi. So there's a big outer loop outside of this whole thing where, with much lower frequency, we'll actually set phi prime to be phi. So that means that most of the time when we're taking this gradient step, we're actually regressing onto a stable target value that is not changing as we change phi, because it depends on phi prime. And then phi prime is still updated because we do want to eventually converge to the minimum Bellman error solution, but it's updated much less frequently. So it's updated like way on the outer loop, where occasionally, let's say every 10,000 steps around this whole cycle, we'll set phi prime to be equal to phi. And then in between, for those 10,000 steps, we'll actually only update phi, which means that our target values are actually not going to change, although we might still collect new data in the process. So we'll be recollecting, we'll be recomputing target values, but still using our old phi prime for that new data. So the targets don't change in the inner loop, which gives us a more stable target. That means that the target that you're regressing onto isn't changing out from under you all the time, which means that this looks a lot more like a standard regression problem, which means that it's much more likely to avoid some of those nasty divergence issues. So now if you actually look at this part of this algorithm, it really looks basically identical to supervised regression. Like you have some target function determined by phi prime and r, neither of which depend on phi within this inner loop, and you're regressing onto that by modifying phi. And then you just have this outer loop where phi prime does get set to phi, and that of course does change the targets, but that happens much less frequently. So now with those two components, with the replay buffer and the target network, we can put together sort of the classic deep Q learning algorithm, which is what you'll actually be implementing for homework 3. So that basically has the target network, this phi prime thingy, and it has the replay buffer. And that's basically it. So if I were to write it out kind of in a more standard way, like the way you might find it written out in the Mini et al. Paper, it basically looks like this. You take some action, AI, and observe some transition. And this is basically the online part. And but then you just store that transition in the buffer. You're not going to necessarily use that transition to learn right away. You're going to put it in memory. Then you're going to sample a mini batch from that buffer uniformly at random. So in all likelihood, this mini batch won't actually contain the transition that you just executed. Then you're going to compute target values for each of the samples in that mini batch using your target network Q phi prime. Not using Q phi, but using Q phi prime. And then you'll compute a gradient to regress from Q phi Sj Aj onto Yj, and average this gradient over all the samples in your batch. And then you'll update phi prime by copying phi into phi prime every n steps, where n might be like 10,000 or so. And then you repeat. Yes?
I would like to ask, I have seen some implementations where the target network is updated softly, like every iteration.
Yeah, so the question was, can we update the target network softly? Yes, and I'll actually cover that in a couple slides, yeah. So with this algorithm, so written out like this, it looks a bit different, but it really is just a special case of this procedure I outlined out here. So for example, if you increase k to be larger than 1, that just means that you want to alternate steps 2, 3, and 4 a couple of times before you collect more data. So that's if you want to raise k greater than 1. You could raise the number of samples over here to be larger than 1, in which case you just you take a few steps before you train. You can do that too. You could even implement this in a parallel asynchronous way, where you just have one thread repeatedly taking transitions and a completely separate thread sampling mini batches. So those are all just variants of this method, and the fit-IQ iteration version is kind of the more general thing, of which this is basically a special case. Okay, and you'll implement this for homework 3. So that's k equals 1. Now, there are other ways to accomplish this goal of trying to stabilize the target values. The goal is just make sure that the right-hand side of this regression, this yj, isn't changing very rapidly. And there are other ways to do that. There are other ways to damp out the updates to the target values. So instead of just flipping the target value every, let's say, 10,000 steps, instead of simply setting phi prime to be equal to phi, you can update phi prime in different ways. So why might it be undesirable to just copy phi into phi prime every 10,000 steps? Well, there isn't really a very formal argument for it, but there's kind of a hand-wavy intuition. And the intuition is the following, that if you're updating every, let's say, 10,000 steps, your training process looks something like this. You collect some transition, you update your phi, collect another transition, update your phi, et cetera, et cetera, et cetera. And then maybe over here, you updated phi prime to be equal to phi. So that means that each of these phi's, they're going to be grabbing their target value from back here. So this guy grabs it from over here, this guy grabs it from over here, this guy grabs it from over here. So they're all operating on target values that have kind of a different age. Like this guy is using a very recent target value, and this guy is using a very old target value. And then maybe over here I flip them. Maybe over here I set phi prime to be equal to phi. So now this guy is using a very recent one. So the recency of the target value kind of goes in these phases. It's not steady over the process of learning, but it gets older, 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 then resets, then gets older, 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 and so on. So it gets a little kind of bursty. And then there's, of course, no lag over here. And some intuition for what's kind of going on here is that essentially every time you flip the target value, you allow the values to propagate one more step backwards, right? Because if you look at this target value equation, it's just setting the target value to be the current reward plus the next Q. If the next Q is garbage, then it's just learning about the current reward. Now when you update Q one more time, now Q is good for one step plus a bunch of garbage. So then you're learning 2 steps into the future, and so on and so on and so on. Like you can imagine as a thought exercise what would happen if the reward was 1 at the goal and 0 everywhere else. Then you're learning kind of a shortest path algorithm, and then the reward will propagate every time you flip the target value by exactly 1 step away from the goal. And so you get this kind of bursty behavior. If you'd like to have information propagate through the system a little more smoothly, what you could do is you could have more continuous updates to phi prime. So instead of updating phi at these very discrete intervals, you can update phi every single time, but damp it out so that update phi prime every single time, but damp it out so that it's changing much more slowly than phi. So one way you can do that and make sure that you always have the same amount of lag is to literally just use a damped update, which is kind of similar in spirit to Polyak averaging, which just means that in step 5, every single time you update phi, you also update phi prime to be a weighted combination of the old phi prime and the new phi. And you choose the weight so that mostly you're keeping the old phi prime, but you're leaking in just a little bit of the new one. So you might choose, for example, tau equals 0.999. So that means that every single time you go around this loop, phi prime is almost equal to the old phi prime, but it's gently nudged in the direction of phi, so you get a damped update. And you would usually use very heavy damping here to make sure the targets do stay stable, but they're still gradually going to chase after the phi and gradually keep up. Okay, but there isn't really any kind of hard and fast rule about which of these works better in practice, and it likely depends on the nature of your problem, how quickly you want to propagate information backwards in time, how much the stability issues are actually hurting you in your particular setting, and so on. And I've definitely seen settings where the soft updates work much, much better, and I've also seen settings where they work much, much worse. Any questions about this? Yeah?
It looks like somehow part of the correlation issue is still here because basically you're always looking at, maybe it's a longer time, but still you're looking at the specific time phrase, and probably the first actions you made, you already forgot about it.
Right. So the question was, it seems like some of this correlation stuff is still happening here. Absolutely, yeah. So as I said at the beginning of the lecture, the fundamental issues with these algorithms are not going to be solved by these tricks. But these tricks will, in practice, mitigate these issues to the point where we can implement them in a computer and have them actually learn something useful. But the issue still persists, the basic underlying problem, yeah. Yes, question back there.
Do people always draw from the batch uniformly? Like, could they skew towards more recent?
Right. So the question is, do we always draw from the buffer uniformly at random, or should we somehow skew this batch in a particular direction? That's actually a very complex question. If you draw from the buffer uniformly at random, then everything is simple and tends to work well, but that's often not the best thing you can do for a number of reasons. First of all, if you're collecting data in step 1 using some modification of your latest policy, like maybe epsilon greedy, then most likely the latest data that you will have collected will be visiting higher reward regions. So it might make sense that you should prioritize picking batches that are more recent because those batches are more likely to contain good experience. So if you're, for example, trying to reach that goal location, the new experience will probably have you reaching the goal more often, which means that they'll have more of the signal that you can back up. You want to be a little careful about that because you don't necessarily want to get too far to the front, because sometimes if your new policy is just very, very good, you'll actually end up forgetting about all the bad stuff that might happen. And you don't want the Q function to forget about the bad stuff either. So that ends up being a very delicate balance in practice. One of the ways that people control that is not actually by modifying the sampling strategy, but by just evicting things from the buffer. So you say, okay, I want my buffer to be to contain 1 million entries, and I'm going to use it as a FIFO queue. So every time something comes in, something gets thrown out of the back. And then you'll have the latest 1 million. That's actually a very common way to design these replay buffers, and that's in fact what you'll all be doing in homework 3. And then the length of that buffer essentially controls the recency of your experience. Ironically, people often find empirically that larger buffers actually work better. So even though it might seem like in the more recent experience is what you actually want that buffer to be pretty large. There's another way to actually be smarter about choosing which experience to sample, which is perhaps a little more ad hoc but can work well in practice, which is to do a kind of hard negative mining. So instead of picking the batches that are most recent, you can actually try to select for batches that appear to have larger Bellman error, basically larger difference between the left-hand side and the right-hand side. And there are a couple of there are a few details on how to set this up properly. It's not quite that simple. You have to actually account for the distribution mismatch and so on with a little bit of importance sampling maybe. So there's some tricks to doing that, and that's called prioritized experience replay if you want to look that up. Okay. So now the last thing I want to do is I want to kind of talk about the relationship between fitted Q iteration and Q learning kind of one more time, just to really solidify this point and draw this algorithm in a graphical way that really emphasizes the fact that it has multiple different processes going on at once. And even though we can write it out sequentially and in fact implement it sequentially, it really is, in a very fundamental sense, a parallel thing. So this is basically the Q learning with the replay buffer and target network, the fitted Q iteration method that we discussed before. It's basically the same thing. Here I wrote it out kind of in a similar notation as above. The only difference is just the ordering of these steps, but for different choices of the numbers here, they probably end up actually doing the same thing. So if you do, for example, soft updates over here, it doesn't matter which order you write them in. And the fact that it doesn't matter which order you write them in is kind of suggestive of something, which is that there's actually just multiple separate processes going on here. There's a process for updating target values, a process for collecting data, and a process for training the network. And those processes can be ordered in some way when you write them out on a page or when you write them out in code, but in reality, they're separate processes. So the inner loop has this kind of SGD thing. There's a network update and so on. The DQN or deep Q learning algorithm is just a special case of this with n equals 1 and k equals 1, which gets rid of these nested loops, which is why that algorithm looked like just one single loop. But larger values of n or k are generalizations of it. So inspired by that, we can also draw kind of a more general view of this algorithm, really emphasizing the fact that there are multiple processes going on. All these processes are centered on your data set, on your replay buffer. And you have one process which is going out and collecting data. So that's process 1. And that just basically executes this step, to collect the data points. So this basically grabs your latest neural network parameters, constructs a policy to do some exploration, maybe by doing epsilon greedy or Boltzmann exploration, goes out, interacts with the world, and brings back some data. And it could just be running here, repopulating your buffer. You have another process, which I didn't really describe in the pseudocode here, but it's just a practical implementation thing, although it can also affect the performance of the method, which is that you have to sometimes evict the old data. So you don't have infinite memory, and you might not want those really, really stale transitions anyway. So occasionally you take the oldest stuff in the buffer and you throw it in the garbage. So that's another thing that can happen. Then you have this, what I'm going to call process 2, which is the target update. So process 2 basically takes care of this thing, the phi prime going to phi. And this process 2 can work in different ways. It can do those damped updates. It can pay attention to how many gradient steps you've taken, and after n steps, where n equals 10,000, it might write phi into phi prime. So there are a few different ways to set that up. And then you have process 3, which is kind of the one that really does the real action, which is the one that's training the Q function. And process 3 is represented by steps 3 and 4. So sample a batch, update on that batch, sample a batch, update on that batch. And you could implement all these processes actually as separate threads if you want, or they can be sequential in your program. But it's important to recognize that they're really kind of just different things that are going on. Yes?
Do you actually want to evict all data, or do you want to just evict the state action pairs that are less rewarding?
Yeah, so the question is, should you be evicting all data, or should you be evicting somehow like maybe the least rewarding transitions? So this relates closely to the previous question about whether you want to sample from the buffer in a smarter way, because how you evict the data versus how you sample from the buffer, they're kind of the same thing in a sense, because anything that gets evicted will never be sampled. Almost always you evict the oldest data. Part of why you don't want to evict transitions that are less rewarding is because you do want the Q function to remember that there is bad stuff that can happen. So if I can fall off the cliff, even though I've now done a really good job of learning to not fall off the cliff, if I completely forget that falling off the cliff is even a possibility, then my Q function will forget that that action has bad value, and then I'll be tempted later on to try falling off the cliff again just to see if it still hurts. And that's probably a bad idea. So while yes, you do want to keep mostly recent, good, highly rewarding experience, you can't simply throw out all the bad stuff. Yes?
Well, won't those like smaller reward transitions have smaller gradients anyways, so like it won't affect the...
Yeah, so the question is, won't smaller reward transitions have smaller gradients anyway? It's important to note that this is actually a difference between the Q and the target value. So if the target value, so smaller reward means negative reward. I guess smaller, the difference is whether it means smaller in magnitude or smaller in like more negative, lower. So lower reward might incur very high error because you might have a huge negative number here and you might not hit it. Rewards that are kind of lower in magnitude, yeah, they'll have smaller gradients, but those aren't necessarily the bad ones. Any other questions? Right. So yeah, so this is kind of the, in my mind, this is kind of the most general view of this algorithm, that once you recognize that there are these processes, you can sequence those processes however you want, and most of the algorithms, most of the Q algorithms, the Q learning algorithms you care to implement are essentially instantiations of this picture in one way or another. So online Q learning from last lecture is just a special case of this, where you evict immediately. So basically, this buffer has a size of 1. Every time you collect something, you throw out the previous thing. Process 1, process 2, and process 3 all run at the same speed in sync. And that basically gets you exactly online Q learning. The kind of classic deep Q learning or DQN algorithm has process 1 and process 3 run at the same speed. So every time you collect a data point, you also take a gradient step, but not necessarily on the same data. And then process 2, the one that's updating these phis and phi primes, is pretty slow, and the eviction happens after, on the order of about 1 million transitions. And then fit-a-Q iteration, kind of the classic form of fit-a-Q iteration, has process 3 running in the inner loop of process 2. So process 3 does a bunch of regression, perhaps even to convergence, and then process 2 updates the target values. So that's the fit-a-Q iteration. And then that runs in the inner loop of process 1. So that's where you get those nested loops. So you regress all the way, update, maybe regress all the way again, update, and then go out and collect more data. So the one that you're going to be implementing for homework 3 is going to be the second one, the DQN, but of course you can modify some of the parameters of that method and very seamlessly get other variants and see how they perform if you're curious. Okay, so now we're going to take a 3-minute break, and afterwards we'll come back to and talk about more advanced topics in Q-learning. So we'll be back at 10:51.
So for my project, I'm thinking of doing like research with like for the Peter Bill.
Okay.
Can I still have a project partner?
A what?
Case? Can I still have a project partner for this one?
Oh yeah, absolutely. So you can also, if you're working with with somebody else on research who is not in the class, you can still do that as your final project. You just have to say that you're working with that person. So even though they're not in the class, we'll count it as like a group of 2 or a group of however many people there are. So what you do is if you're doing a research project, just submit the proposal as normal and just say that you're working with this person, just so we know how many people there are.
I think it's probably the PhD student who's the kind of partner, but can I also have a partner from within the class?
Yeah, absolutely.
Oh,
yeah,
okay.
that's fine.
Okay.
So just as long as you tell us everyone who's involved in the project.
Okay, thank you.
In the epsilon greedy, you have to get divided by the number of actions somehow, and that's why I asked you infinite or infinite. Because
Oh, okay,
it's,
yeah.
It seems the tabular case,
Right.
but it's not.
So you can do the equivalent thing for continuous actions or for infinite numbers of actions. For continuous actions, it amounts to saying that I'm going to mix a uniform distribution over actions with a Dirac delta. So that the resulting distribution looks like a slab and a spike. That's a perfectly legitimate distribution to sample from. If your actions are unbounded, then of course you can't have a uniform distribution. Then you would use something like a Gaussian or something like that. But yeah, it's totally fine to use a uniform over a bounded interval. In practice, for some reason, people don't usually do that for continuous actions, just because I think Gaussian distributions are much easier to deal with. But you could use uniform distributions if you want.
Okay.
All right, let's continue. So in the second half of today's lecture, I'm going to talk about a few more advanced techniques that we can use to further improve Q-learning. I'm going to talk about actually a couple of things. I'm going to talk about double Q-learning and step returns, and then I'll talk about some methods to use Q-learning for continuous actions. And then I'll conclude with a discussion of some research papers that have used variants of Q-learning algorithms or fitted Q-learning algorithms in the past. So one question that we could ask about these Q-learning algorithms is, well, are the Q values that are being learned actually accurate Q values? So if you remember the discussion from when we started talking about these value functions, Q values actually have a meaning. What Q values are meant to represent is the total reward that you will get, potentially discounted total reward, if you are in some state S and take some action A and then follow your best possible policy. Not your exploration policy, but your best possible policy. So are Q values accurate? What I'm showing with these plots are some experiments with Q-learning with a deep neural network function approximator on Atari games. And the way to look at these plots is that this one is showing the actual reward attained as a function of the number of training iterations on the x-axis. So the y-axis is actual total reward, x-axis is training iterations, and this is learning to play the game Breakout. And you can see it's going up, which is good. That's what you want to see. So you should see something like that on your homework too. It should go up. It's kind of spiky, so sometimes it suddenly does better, suddenly does worse. There's a little bit of randomness, but generally seems to be going up. Now the second curve, same thing. X-axis is number of training iterations, y-axis is average reward, and this is on the game Sequest. It's kind of a fun Atari game where you're supposed to pilot a submarine and shoot fish for some reason. These two plots, this is for the same games, this is Breakout and this is Sequest. And what these are showing are the average Q values. So remember that if you take the Q value in the initial state and you take the expectation of it under your policy, which is very easy to do because the policy here is deterministic, so you just pick the Q value for the best action, that actually should give you an estimate of the expected reward that you'll get. So that's what you'd expect these quantities to represent. And unfortunately, the people who drew these plots normalize things in weird ways, so the numbers on the y-axis actually don't mean anything. But you can see that both of them seem to be going up. So that's kind of good news. This is going up, and this is going up. So you're predicting that you'll do better, and you indeed end up doing better. That's what we'd like to see. So the predictions seem to kind of correlate with reality. So as predicted, as the predicted Q increases, the return also increases, which is good. And in fact, you can plot, the Q function or the value function derived from the Q function. The way you derive the value function is just by taking the max over actions. So you can plot these things, and you can actually look at which states have higher values, for example. So this is the game Breakout. The objective of the game, for those of you that aren't familiar, is to use this little red paddle at the bottom to hit a ball, and the ball it breaks the bricks when it hits them, and you're supposed to keep the ball bouncing and break as many bricks as you can. And one really cool thing to do if you're a real pro at this game is to punch a little hole in the whole stack of bricks and hit the ball so it goes through that hole into the top, because then it'll bounce around a whole bunch and give you lots and lots of points. And then you can impress all your friends. If your friends are from 2 decades ago. So what you can see here on the bottom, this is a plot of the value function. The x-axis actually now represents time. So this is just playing a single episode. So here you started playing, and the pictures at the top basically represent what the game looks like at that point in time. So here at the beginning, you're just breaking a brick. So number 1 here, this point corresponds to this image. So you can see that when you're about to break a brick, there's a little spike in value. It says, oh, I expect the good stuff to happen. Here it comes. The points are gonna come. And then here, you're about to break a brick again. Again, there's a little spike, and it says, oh, the points are going to come. But here, you kind of messed up a little bit because your paddle is way over here and the ball is way over here. So right afterwards, the value dips a little bit because it's like, oh, okay, great, I broke a brick, but now I'm going to drop the ball, and that's not good. So there's something sensible going on. And then over here, this is the interesting bit. So here at the end, he managed to kind of break through this stack of bricks and get the ball up to the top. And you can see that the value function is going up. It's going up a lot more than than the reward you're actually getting at that point, because it's anticipating that future reward. It's anticipating the fact that as soon as it breaks through here, this thing is going to break a ton of bricks and get lots of points. So even though it hasn't actually done that yet, it's broken through, but it hasn't gotten the points yet, the value function is already high. The value function anticipates future reward. So actually getting the reward is not what correlates to high value. It's the point at which you're sure that you're about to get the reward. So here it's determined, okay, absolutely, I'm definitely going to get that reward. This is the peak of the value function. From here, it's only going to go down, but the points are about to start arriving. So things kind of make sense. The value function, as expected, seems to predict future rewards. The Q function also does something reasonable. This is the game of Pong. For those of you, again, that aren't familiar with it, the objective of the game of Pong is to control the green paddle to hit the white ball so that it ricochets back, and it's like tennis, so you're supposed to ricochet it back so that the other guy can't use the orange paddle to return it to you, but instead it goes out and you get a point. And what I'm showing at the bottom here are the Q values now. So the yellow bar represents the value associated with the action for doing nothing, for keeping the paddle where it is. The purple one is the value associated with moving up, and the magenta one is the value associated with going down. Over here, it's kind of funny, like why would this be the case? The Q values are all about equal. But that's because the policy knows that when the ball is over here, there's enough time to get the green paddle to the right location. So even if you don't take the right action right away, at the next time step, you'll still have time to reach the ball. So the Q values are actually kind of flat here. But now the ball has gotten closer, and now the Q value for the up action is much, much higher, because now the policy is thinking, well, if I don't press the up button now, I'm going to lose. So I got to press it right away, otherwise I'm going to not get the reward. And that's the case here too. Like here, you can maybe just about save it if you move up, so it's really high for the up action. So things seem to make sense. Values predict rewards. Q values seem to kind of suggest which actions are good in a way that corresponds to what we expect.
Questions?
Yes?
So what if that kind of actions is not in the replay buffer?
Yeah, so the question was, well, what happens if this kind of state or these kinds of actions are not in the replay buffer?
I mean in breakout.
Oh, in breakout. Right. So the usual story with that is that you need to have your data kind of statistically representative of what you're actually going to see at test time. So if you've never ever seen the ball bounce to the top like this and get you lots of points, then of course you won't be able to make accurate predictions. But you are training a function approximator. So perhaps you've never seen the ball go to the top with just this particular configuration of broken bricks. Maybe you've seen this happen, but the bricks at the bottom were a little different and so on. Well, then you'd expect your function approximator to be able to generalize. You'd expect it to be able to recognize that the ball being at the top like this is much more important than which bricks are broken at the bottom. And that's just the generalization. Yes, question back there.
When you're learning the Q values the first time or the first few times through a given action in a state, you have a lot more exploration information about what the reward is, what the next state is. For the next or subsequent times you take that action, you'll derive less of that reward. Does the Q function account for that?
Could you repeat your question?
Right, so let's say it's when you take a reward, when you take an action, you expect some reward plus some variance of that reward, like UCB sampling of what the rewards will be. So each time you take that same action in the same state, your uncertainty will go down, so your information of doing that action will go down.
Right. So generally for MDP problems, we actually assume that rewards are a deterministic consequence of states and actions. You don't have to make that assumption. So for example, you could assume that rewards have some distribution and the parameters of the distribution are uniquely determined by the state and action. That's a very common assumption, for example, for bandit problems. We'll come back to this later on when we talk about exploration, and we'll actually discuss bandit problems in depth. But for almost all RL algorithms for MDPs, they actually make the assumption that the reward is a deterministic consequence of states and actions. In all cases, if you're ever faced with a situation where the reward is stochastic in the state and action, solving the problem where you use the expected value of the reward is precisely equivalent to solving the original problem with the stochastic reward. The reason that for bandit problems we often try to explicitly model this distribution is that for bandit problems, just identifying what the distribution is considered challenging. That's kind of the objective. But usually for sequential decision-making problems, the sequential aspect of it gives us so much trouble already that we don't even bother worrying about stochastic rewards. But if you do have stochastic rewards and you run this algorithm, it will actually do the right thing. It'll optimize for the expectation of the reward. All right, so this was kind of the good news, that value function precedes reward like we expect, and the Q values give us something reasonable. But are they actually numerically correct, right? The average reward that you get when you run the policy, that is a number. You can measure that number. And the reward that is predicted by your Q values, that is also a number. And you can look at these two numbers and see, are they the same? Are they equal? And it turns out that if you run these Q-learning algorithms with deep neural networks, quantitatively, these values don't actually agree. So ignore the blue stuff for now, just look at the red stuff. And let me explain to you what the red stuff is showing. So the kind of spiky, noisy red curve is showing the estimate of the return from your Q function. This is how good does the Q function think your policy will be when you run it for a single episode on average. And these are 4 different Atari games. And for each of them, the Q values, well, I guess for each of them except for this one, which I guess something weird happened here, for each of them the expected Q values go up. So the thing predicts you're going to do better and better and better, and over here you'll do really, really well, and over here you'll do well, and so on and so on. And then the straight line, it's a slightly weird visualization, but the straight line shows you the average reward that you actually get at the end. So the reason it's a straight line is just it's for the end here. So what this is showing is that the red line, it's pretty much always much, much lower than the estimate that you're getting from your Q function. If I had a full curve of the average reward, I would expect it to also go up. It just doesn't go up to the same number. It ends up much lower. So what's going on here? For some reason, the Q function thinks that you'll get a much bigger reward than you'll actually get. So we saw before over here that they do both go up. So the trend is kind of the same. There's some correlation. But the numbers, with the numbers, for some reason, the Q function is just very optimistic. It thinks you're going to do way better. So why might that be the case? There are some pretty complicated reasons why this happens, but there's a relatively simple explanation that sort of gives the bulk of the intuition. And the simple explanation has to do with what happens when you take the max of a collection of random variables. So in Q-learning, the way that you compute your target values is you take a max over possible actions. Now, your Q function is not perfect, and one of the ways that you can very crudely model this imperfection is to say, well, your Q function kind of has reasonable values plus some noise. Not actually a great model because it's not really noise, it's just errors in your fit, but let's very crudely think of the errors as noise. So maybe action 0 should really have a value of 17.5, but your Q function estimates like 18.3 because it's a little off. And action 1 should be 17.4, but your Q function estimates like 16.1. Right? So it's just a little bit off. Sometimes a little higher, sometimes a little lower. But when you take a max, you're going to exaggerate the mistakes where the Q function is bigger than it should be. So the problem is this max term here. Let's imagine that you have two random variables, x1 and x2. And these random variables will represent the value assigned by your Q function to action 1 and action 2 at a particular state. The expected value of the max of these two random variables is always greater than or equal to the max of their two expected values. This is it's a very simple fact. If I had a marker, I could draw it. So basically, if you have two noisy functions, one that goes like this and one that goes like this, right? Both of them have an expected value that's basically a flat line. So the max of their expected values is this flat line right here. But the expected value of their max basically amounts to taking the curve that is the upper one of the two, like this, right? So it's the upper one. And its expected value is much higher. Does anyone have any questions about this expected value of max thing? Okay. So since the expected value of the max of these two variables is always greater than or equal to the max of their two expected values, you're actually going to get overestimation from this. You're going to basically get the upper of these two curves, which will exaggerate the positive noise and undervalue the negative noise, or exaggerate the positive errors. So since these Q values are kind of not perfect, they kind of look a little bit noisy, then the max actually overestimates the next value. And now we'll talk about some ways to mitigate this issue. And in talking about ways to mitigate this issue, one very important property that we need to take note of, which will actually become useful also later on when we talk about continuous actions, is that when you have a max, this is kind of a silly way of writing it, but if you have a max over A prime of Q S prime A prime, that's the same as Q of S prime and argmax for the action. Right? That's just saying this max, this is the value of a policy given by the argmax. Kind of a trivial statement, but it turns out to be very useful for allowing us to mitigate this problem. Okay. So the trouble that we're having when we write it like this is we can view it as the problem that our value comes from q phi prime and our action comes from q phi prime. So we'll choose the action. So if q phi prime is a little over optimistic about some action, we'll choose that action and we'll use its over optimistic value. So one of the ways that we can greatly mitigate this issue is by using a technique called double Q learning. So in double Q learning, what we're basically going to try to do is we're going to try to decorrelate the noise in the action selection from the noise in the values. So if we had two functions, like the ones I drew here, that were whose errors were not necessarily correlated with each other, but that both had errors, then perhaps we could use one of them to pick the action and the other one to get the value. That way the noise actually kind of cancels out. The noise doesn't actually add up like this to over-exaggerate the positive errors. So that's basically the idea behind double Q learning. It's called double Q learning because we're going to have two Q functions. And the goal of having those two Q functions will be to decorrelate the value from the action, meaning decorrelate the errors in the value from the errors in the action. So if we don't use the same network to choose the action as the one that we use to evaluate its value, then maybe this overestimation of errors problem can be addressed. So we're going to have two networks. We'll call them phi A and phi B. And we're going to compute the target values for phi A by using network phi B to evaluate the value and network phi A to choose the action. So we'll try to update phi A so that it moves towards R plus gamma Q of phi B with the action taken by phi A. So since we're taking the action using one network and evaluating its value using the other network, if they both make mistakes but those mistakes are not correlated with each other, then we shouldn't get the overestimation issue that I described before. And then phi B the same way. It'll be updated using the value from phi A but using the action from phi B. Does anyone have any questions about this scheme?
It is easy to check.
Say that again?
It is easy to check because you have two networks, right? So I think it's hard to check.
Right. So the question was, well, there's two networks. Do you have to train two networks? The answer is, in the classic double Q learning algorithm, yes, but there's a little simplification that we'll make on the next slide that will address this.
You're going to use also again the older one?
What's that?
You're going to again use the
Yeah.
older version?
Yeah.
One thing that is confusing here is that what are the inputs and outputs of each of these like networks? Is it like state action pairs and?
Oh, there's a typo on the slide. Yeah. So this should say S prime comma A prime, and this should say S prime comma A prime.
So the input is both state and action.
Yeah. Sorry, there's just a typo. Yes.
Is there any particular reason why it's like Q5B then argmax? Or could they be swapped?
Oh, you mean if you just flip these?
Yeah.
Yeah, you could do that. So this is not really saying anything about what you should do with those target values. This is just giving you a better way to compute the target values. Okay. So yeah, if the two Q functions are noisy or erroneous in different ways, then this problem in principle should go away. Of course, the noise isn't really noise, it's errors, and those errors are sometimes caused by systematic things, so in practice this doesn't totally eliminate it, mainly because this is kind of only a crude picture of what's really happening, but it can mitigate it. So in practice, the way that we could actually implement double Q learning is much simpler than this. We don't really need to train twice as many networks. We can get two Q functions in another way. It will introduce some additional issues. It's not perfect, but it's very, very simple. And the place that we can get those two Q functions is by using our phi and phi prime. So we can just use the current and the target networks. They are not completely separate from each other because, of course, the way that we get phi prime is by periodically copying phi into it. But maybe they're different enough to decorrelate these things just enough to mitigate that overestimation problem. So in standard Q learning, we compute our target values like this, and here I've just swapped out the max and instead put an argmax, but you know that those are exactly equal. So your target value is R plus Q of phi prime, S prime, comma, argmax of Q phi prime. That's the same as the max over Q phi prime. Here, we're going to now turn this into double Q learning using phi and phi prime as our phi A and phi B. And that'll get us this update. We'll just say that the target value is R plus gamma Q phi prime, where the action is evaluated using Q phi. And you don't need the opposite one because you're only updating phi. You're not phi prime is just a lag copy of phi. So you only need to update phi like this. Phi prime will naturally get updated when you flip the target network, and this gives you much of the benefit of doing double Q learning. So literally the only change we've made is we've turned this prime, this phi prime, into a phi. Done. It's a very, very simple modification. So that's it. That's just that thing. So it just amounts to saying, let's use the current network, not the target network, to evaluate the action, meaning pick the action, but the value of that action still comes from the target network. OK, so this is double Q learning. We'll actually have a little section in homework 3 for you to implement double Q learning. It's a very, very simple modification. It pretty much always helps, and it's so easy to do that there's kind of no reason not to do it. Of course, it's not going to totally solve the overestimation problem because this expectation of the max versus the max of the expectation is only a crude model of what's really happening, and we're not using two totally independent models anyway. So it doesn't totally solve the issue, but it actually reduces it considerably. OK, the other trick I'm going to talk about today is something called multi-step returns, which is closely related to something we discussed before for actor-critic algorithms. So let's throw up that equation for the target value again, and I'll go back to using this max just to declutter my notation a little bit. So the target value is the reward at that time step plus the next Q value. Now, where does the learning signal actually come from when you train your network on these target values? Well, where the learning signal comes from depends on how good your Q values are. So if your Q values are good, meaning that they're reasonably accurate, then you would expect most of the signal to come from here because the future rewards, the total future rewards are probably bigger than the reward right now, right? Because there's a lot more future. There's only one current time step, and there are many, many future time steps. So if you have an accurate Q function, you'd expect the bulk of the learning signal to come from the second term, because that term is just going to be bigger. But if your Q function is terrible, then there might not be anything to learn from that second term, and the bulk of the learning might come from the first term. Right? So if your Q function is bad, then it's really only that first term that matters, because that's the real reward. And this is kind of a similar issue to what we saw before when we talked about actor-critic algorithms. So for actor-critic algorithms, we talked about how we could do fully bootstrapped updates, where we use the reward plus the next critic, or we could do fully Monte Carlo advantage estimates by summing together rewards. So Q-learning basically does the fully bootstrapped version. And as we discussed for actor-critic, this gives you the maximum bias, but the minimum variance. Right? Maximum bias, because if your value function or your Q function is incorrect, you have incorrect estimates, but the minimum variance, because all these summed rewards, these are single sample estimates, whereas the value function or Q function is an estimate of the full expectation. So that's what Q-learning is doing. It's the max bias, minimum variance. But we don't have to do this. So we saw in the actor-critic lecture that you could actually sum up a few rewards and then put in the value. And you could do the same exact thing with Q-learning. You can construct multi-step targets, just like an actor-critic. By constructing your target value to be the sum, there's a discount factor that's missing. That should be gamma to the t prime minus t times the reward at time step t prime plus the max after n steps. So you do gamma to the n times the max n steps into the future. So this is referred to as n-step returns. It means sum together n rewards with discounts and then add in the value after n steps. Now, this, if your Q function is terrible, this will give you a better estimate of the target value because the rewards are actual rewards, but the Q values are just garbage. If your Q function is great, then this will give you a higher variance estimate because these rewards, even though they're true rewards, they're just one of many possible futures that could have happened because your transitions are stochastic. There is another problem, though, with using n-step returns for Q-learning. So this is the n-step return estimator. The trouble, well, OK, so the good thing is that you get less biased target values when the Q values are inaccurate. It's typically actually faster, especially early on, because early on your Q values are usually terrible. The downside, and this is something that is a downside that's actually specific to Q-learning. We didn't see this downside for actor-critic. The downside is that this is actually only correct to do when you're learning on policy. This is a little subtle. So with actor-critic, we were always learning on policy, so we never had this question come up. With Q-learning, we typically use off-policy data, data that came from a different policy. So why is this a problem when we're using n-step returns? Does anyone have any guesses? Yeah?
Well, you're taking a bunch of rewards in a row, so they have to come from the same policy, otherwise it just doesn't make sense.
Right, so the answer is, well, you're adding together a bunch of rewards here, so they have to come from the same policy, otherwise it doesn't make sense. So if you were using like a random policy, then this isn't an estimate of the reward of your current policy, it's an estimate of the reward of a random policy. So which policy are you trying to estimate the Q values for? Well, you're trying to estimate the Q values for this policy, the one that takes an action with probability 1 if it's the argmax and 0 otherwise. But these rewards came from some transitions that came from a different policy. Even if it's just your exploration policy, it's still a different policy. So this is supposed to estimate Q pi for pi, this pi, but if you're using off-policy data, it could be any pi. So you need transitions that actually come from your current policy pi. This wasn't an issue for one-step Q-learning, because for one-step Q-learning, you're conditioning on the state and action of that step. But for n-step, you're still only conditioning on the first state and action, but you're adding together the rewards for future steps, and you're not conditioning on those actions. So there's not an issue when n equals 1. So how do we fix it? Well, there are a couple of different fixes for this problem. So one fix is to ignore the problem. And it's OK to do that if you use small values of n, and your actions are, they change the system in some small way. So if you're learning, for example, to play Atari games, and you use like n equals 4, probably it'll actually be fine. Because within 4 steps, even though different policies can do different things, they're kind of close enough that it kind of washes out in the noise. And the faster learning actually gives you a lot of benefits still. So ignoring the problem often works very well, especially for small n. Another thing you could do, which is a little more principled, is you can cut the trace, which means that you actually stop the summation. You don't stop it after n steps. We actually stop it as soon as you see an action in your buffer that is different from what your policy would have done. So if it just so happens that you did exactly the same thing that your policy would have done anyway for 4 steps in a row, then sum up the rewards for those 4 steps. But if you didn't, then stop as soon as you get a transition with an action that is not the one you would have taken, and instead put in the Q value there. That's a very reasonable way to make things unbiased, but of course, it doesn't really work very well when you have a huge number of actions because the probability of taking the right actions is so low. But for like Atari games where you have like 3 actions, it's reasonable. Was there a question?
Yeah, I was just going to say, like, it doesn't seem to really work if you have like a stochastic policy or something. Or, like,
so the question was, this doesn't seem to work if you have a stochastic policy. That is true. Of course, in Q-learning, you always have a deterministic policy. So Q-learning is trying to estimate the value of a very particular policy, this one. And this one is always deterministic. All right, so it works well when the data is like mostly on policy and the action space is small. So maybe you have a smaller replay buffer. Most of the data kind of came from a policy that's close enough to this one anyway. And the action space is small, so the probability of randomly just taking the right actions for multiple steps is not too low. Then this could actually work decently well. And then there are more complex solutions. For example, you could use importance sampling. You could do some combination of cutting the trace and importance sampling. So there's a variety of different fixes to this issue. And if you want to see a more in-depth discussion, check out this paper called Safe and Efficient Off-Policy Reinforcement Learning by Munoz et al. OK, so that's n-step returns. And then the last thing I'm going to cover, the last technical topic, is Q-learning with continuous actions. So far we've only talked about discrete actions, but you can actually use Q-learning algorithms with continuous actions also. And there are actually a few different options for how to do this. So first, what's the problem with continuous actions? The problem with continuous actions is that your policy is given by this argmax. So you need to figure out how to take the argmax of your Q function. So this max is very easy to do if you have a small number of discrete actions, because you compute the Q values for all of your actions, and then you take the largest one. Right? And the same problem happens also for the target value. For the target value, you also need the max. And that one is actually perhaps more important, because if you're using a batch, you evaluate this max much more often than you evaluate this max. All right, so how do you perform this max for continuous actions? For continuous actions, you can't just try all possible actions because there are infinitely many of them. So you have a number of different options for approximating this maximization. One option is to use some decent optimization algorithm, like literally plug this into some optimizer and find the A that gives you the largest Q of S comma A. Gradient-based optimization, like SGD, can be a little slow in the inner loop of training because, remember, for this thing, for the target value, you have to do this for every single gradient step. So if you have to run a gradient-based optimization for every gradient step you're going to take, that's going to be pretty slow. But if you can afford it, then it should work. But your action space, even if it's continuous, is typically low dimensional, usually lower dimensional than your state at least, lower dimensional than like image observations or something. So you could use some stochastic optimization procedures that can actually be quicker for low dimensional spaces than running gradient descent. So let's talk about Q-learning with stochastic optimization for that max. So a very simple solution is to approximate the max over the continuous action as a max over a discrete set of actions. And then you sample that discrete set from some distribution. If your action space is small enough, this can actually work pretty well. So you sample some discrete set of actions, A1 through AN. Maybe you sample 64 possible actions, and you take the Q value that is for the largest one. This will not give you a very precise max, but it will probably give you a pretty decent action. So it's dead simple. It's very easy to implement. It's efficiently parallelizable because in most automatic differentiation packages and most neural network packages, you can evaluate a batch over actions. So you can just treat A1 through AN as different entries in a batch and evaluate everything in parallel. It's not very accurate. So especially as the dimensional gets larger, this is not going to give you a very precise estimate of the max. But it's a reasonable and simple solution. And also, do we care that it's not very accurate? Like, how good does the target need to be anyway? We talked before about how overestimation seems to be a big problem, so maybe not having such a strong max is okay. And in some cases it is okay, but in some cases you pay a price for it. There are more accurate solutions that are very similar in spirit, but can give you a much better max. For example, you can use what's called the cross-entropy method. We'll talk about the cross-entropy method in more detail later on when we talk about optimal control, but it's basically a very simple technique that just samples a bunch of A's like this, and then instead of taking the max right away, it actually fits a new distribution to the top percentile of those samples, and then repeats the process. So it's a simple iterative stochastic optimization procedure. You can use more advanced stochastic optimization procedures like CMAES and so on. I'm not going to cover those in detail right now, but I will talk about them a little more when I talk about planning and optimal control later. Question?
Why the sampling is from some distribution and not from the actions taken by what you're training?
Yeah, the question is, well, why are you sampling from some distribution instead of maybe the actions that your policy would have taken? So remember, the goal here is to evaluate the value of your policy, but your policy is given by this max. So solving for this max is the process of getting your policy. So if we don't know anything else, basically the best that we can do is we can sample from some distribution. You can adapt that distribution. It doesn't have to be uniform, and that's actually more or less exactly what cross-entropy method does. It actually adapts the distribution to be closer to the region with good actions. Okay. There is another option, and this option is actually exact, but it's disappointing in some other ways, which is to use a function class where it's easy to maximize with respect to A. And there are some function classes that limit your representational power, but make it very easy to take that max. So one example, and this is something called normalized advantage functions, is to use Q functions that are still given by neural networks, but that are quadratic in the action. It doesn't have to be quadratic, it can be some other function that's easy to maximize, but quadratic is particularly simple. So if your neural network outputs a matrix, a vector, and a scalar that together form a quadratic function in A, so it's not quadratic in S, it's some complicated neural net function in S, but it's quadratic in A, then you can maximize this with respect to A analytically, because the optimum point for a quadratic function can be solved just by solving a system of linear equations. So this is called normalized advantage functions. And then your argmax, in this case, if you parameterize it using p and mu, your argmax is just mu, and your max is just the scalar component v. So this involves actually no change to the algorithm. You don't need to add any other additional kind of fancy sampling or stochastic maximization. It's just as efficient as Q-learning computationally because you literally just write the number in here and the number in here. But you lose some representational power. So not all problems have Q functions that are quadratic in the action. So there's some additional approximation going on here, and maybe you really want that representational power. Maybe the reason that you're using neural nets is because you want to be able to represent really complex functions. So that's a price that you pay here. But the gain is in simplicity. You can also do Q-learning with continuous actions in another way. This is option 3, which is to learn an approximate maximizer. So this option 3, it's kind of a compromise between option 1 and option 2. It's going to try to maximize. It's going to have any function approximator, but it's going to do the maximization approximately, but without running something at runtime. So the particular algorithm in this category that I'm going to discuss is called DDPG, but there are a number of methods that all are based on the same principle. So the idea behind DDPG, it's sometimes actually referred to as a deterministic actor-critic algorithm, but it's really an approximate Q-learning method with an approximate maximizer. And here's how it works. So remember that this max over Q, you can equivalently write it as Q of S comma argmax. So all you really need to be able to do is evaluate the argmax. And then once you can evaluate the argmax, you plug it into the Q function. So the idea is that instead of actually evaluating that argmax with some kind of optimization, we'll actually train a separate neural network to approximate the argmax. This is like the deep learning solution. When in doubt, just train a network to do it for you. So we're going to call this network mu theta. And that network is going to be a policy. It's going to be a deterministic policy. And its job is going to be to approximate this argmax. Does anyone have any ideas about how we can train mu theta? Yes?
You just take the gradient.
The gradient of what?
Q5, that's it.
Okay, so the answer was just take the gradient of Q phi with respect to the action. That's exactly how we're going to train mu theta. So mu theta is supposed to be the argmax, so you just solve this optimization problem when you train it. Now, critically, unlike option 1, you're not solving this optimization problem every time you compute target values. You're solving this optimization over all of your samples to get mu theta, and then every time you want a target value, plug mu theta in place of the argmax. So you train theta with gradient ascent, and the gradient is just obtained from the Q function. So you take dq dA, dA d theta. dA d theta is obtained by backprop through mu, dq dA is obtained by backprop through Q. So you just backprop through both of your networks, and that gives you the gradient with respect to theta, and that allows you to train up this mu in order to get it to be close to the argmax of Q. So then your targets are just obtained by plugging in the mu in place of the argmax. So concretely, the DDPG algorithm looks like this. You take some action and observe a transition added to your buffer, just like in regular Q-learning. Then you're going to sample a mini batch, just like in regular Q-learning. Then you're going to compute your target value, but now you're going to use mu in place of the argmax. So this is a typo again, please ignore this max. It's just Q phi prime, S prime, mu theta prime, S prime as the argument. Both Q and mu have a target network version of them. So the reason I'm calling this Q phi prime and this mu theta prime is that they're both using the target network parameters. You update your phi the same way that we did in the Q-learning algorithm. We're going to just compute the gradient of the difference between the Q value and the target value. But then we're also going to update the parameters theta, the parameters of mu. And those parameters will be updated by backpropping through Q and then backpropping through mu to try to make the Q value of mu of S as large as possible. And then you're going to update the target network parameters phi prime and theta prime using whatever target network update you want, either the Polyak averaging thing or doing the hard update every n steps. So that's the DDPG algorithm. Okay, was there a question?
Yeah. So in other words, basically we have two neural nets. One is basically learning the orders of the Q values, and the other one is actually learning the values of them. Like one cares about the orders, not the actual accurate values, but the other one is actually learning order values.
Right. So it's a little bit different than that because mu doesn't really tell you anything about the ordering of the actions. It's just trying to find the argmax. So it doesn't know who's the second best, who's the third best, who's the fourth best. It just wants to know the single best action. And that's very different from the kinds of policies that we talked about when we discussed actor critic and policy gradient, because those were stochastic policies. This is a deterministic policy, and all it's trying to do is find that argmax. Okay, some practical tips for Q-learning, just to conclude. So Q-learning takes some care to stabilize. So when you're implementing your algorithm, for example, when you're implementing it for homework 3, test it on easy, reliable tasks first that you're sure are easily solvable, just to make sure your implementation is correct. Because iterating with Q-learning on really complicated tasks can take forever. And actual correct implementations can still produce some pretty wacky results. These are learning curves for a number of different Q-learning algorithms from a paper from 2015 that's analyzing a particular experience replay technique. And on some games like Pong, this is something you'll do for homework 3, it's a very nice clean curve. For some other games, it's a complete disaster. So this kind of stuff happens, like don't be surprised by it and be very patient. Large replay buffers tend to help improve stability. So even though it might seem like you don't need to store a million transitions, it can help make training more stable. It makes it basically look more like fit a Q iteration in a sense. And it takes time, so you should be patient. And it's normal for these algorithms to kind of be flat in the beginning and to take a while to pick up. So if you're used to writing SGD to do supervised learning, you expect the error to drop massively right at the beginning and then plateau. With these things, you get things that look more like an S-curve. So you'll get kind of nothing for a while. Then as the exploration picks up, as it actually starts finding those high reward states, then learning will start going up, and then it will plateau again at the top. So don't be surprised by that, that's normal. It's a good idea oftentimes to start with very high exploration. So if you're using epsilon greedy, maybe start with a large value of epsilon and then gradually reduce it. It might help to play with learning rates a little bit too, and also adaptive step size adjustment rules like Atom can help a lot there as well. Some advanced tips just to wrap up. So the error of the gradient of the Bellman error can be very large because the Bellman, we're using basically the gradient of a squared Bellman error. So the derivative of a quadratic can be a very large number. So it often really helps to clip the gradients when you're using Bellman error as your regression objective. One thing that ends up doing something very similar to clipping the gradient is to use a Huber loss instead of squared error loss on the regression step. So Huber loss basically looks like absolute value until it gets to the bottom, at which point it has a little curved cusp to make it differentiable. Double Q learning helps a lot in practice, and it's simple and has basically no downsides, so you should just use it. N-step returns can also help a lot, but they do have some downsides because for off-policy learning, they're technically incorrect. And then, yeah, the exploration I already mentioned and the adaptive optimization. Also, Q-learning tends to do very different things between different random seeds, so do test multiple random seeds if you want kind of statistically significant results. All right, I'll stop there and see you all on Wednesday.